Good morning, everyone. So I'm going to talk about the analysis of GNSS receiver biases and noise using zero baseline techniques. So just a quick overview. We have a test site at Shirley's Bay in Ottawa, and we've set up all this hardware that I'll talk about in a minute. Now, the purpose of this talk is to specify interoperability between receiver types for GPS, GLONASS, and Galileo, not to rank receivers, not to measure precision. So I just want to get that out of the way right away. So I'm going to talk about the receivers used and the signals tracked, GPS, GLONASS, and Galileo. Now, we used MSM7 data and converted it into RINEX. I have to say not all receiver types encoded the data correctly, so there will be some gaps in the data. So we determined code biases between receivers tracking the same signals. We also did phase alignment between GPS and Galileo using common signals, common frequencies. And we made an effort to estimate phase noise, and I'll have a quick summary at the end. So this is the setup. We have a modified AOA antenna with a GNSS LNA. We have a signal splitter, and then we have the receiver types that you see. We have a septentrial polar RX5, which we use as our reference receiver, a Novotel OEM6, TrimbleNet R9, a Javad Delta 3N, and a Topcon Net G5. So these receivers don't all track the same signals. You can see that for GPS, we pretty much have common signals. CA and the CA and P1, or P1 is only tracked by the septentrial, the Javad, and in this particular case, the Topcon doesn't track P1. It tracks it, but it doesn't encode it. That's going to be an improvement in the next firmware release. We have common signals for GLONASS. Now, on the Galileo side, we have the septentrial tracks the Q signals, and then as does the Novotel, and Trimble and Javad track the X signals. So those are differences that we'll have to account for. One thing I thought we'd show would be the effective SNRs. And so, like I said, this is focused on interoperability. So I wanted to say a few key words here. You'll see that the SNRs between on the GPS side vary significantly. They're not between receiver types. They're not the same, and that the Novotel has a very narrow SNR range. On the Galileo side, they seem to be more common. The entry level of tracking and the maximum signal to noise ratio is more similar. Okay, so how did we come up with these code biases? What we did is we formed single difference observations, phase and code between receiver X and the septentrial. And that cancels the satellite and atmospheric errors. We estimated between receiver clock offsets and carrier phase ambiguities, and then we averaged the code residuals per satellite over each day to obtain code biases. Then we averaged code biases over 7 days and computed standard deviation. So I know it's hard to see this one, but trust me, I have another one where it's blown up. So the first one, you have the Novotel septentrial, and across the bottom is all the satellite numbers. And you can see that you have C1C, C2W, and C5Q biases. So the Novotel fits the septentrial quite nicely. And then we have the Trimble septentrial where the fit isn't quite as good. And the Javad and septentrial, which are very compatible receivers. They're P1, P2 tracking receivers. And you can see that there are still some significant differences. And then we had a configuration error with the TOPCon Net G5 where we had CA code multipath mitigation turned on, so we have large biases there. So I thought we'd show one where we don't have such a good fit, which is the Trimble septentrial. And you can see that the biases are large, up to 0.3 of a meter. So, and then, as I said, the standard deviation over the week of averages is shown by the little arrow bars at the end of the bars. So we had a very good fit over the week. Now, I think that something that's important to say is that the differential code biases that are estimated by everyone, I believe, assume that the receiver types are compatible, so that the L2W and L1W values are similar. I think from what we've seen here, they're not really similar. So the DCBs will have noise and maybe biases. So here's the compatible receivers. I believe that these, the Javad has been widely used in the IGS. It's a P1, P2 tracking receiver. And we have a bias as high as almost 0.3 for, I think it's G25. So and other, there's 0.2, 0.3 of a meter. Now, I'm not going to say too much about the GLONASS code biases. The results that we obtained were pretty much in line with the results that have been shown earlier by others. Similarly, the phase interfrequency biases are more or less the same as others. Okay. So Galileo code phase biases, I think the story is a little better here. You can see that the fit between the Novotel and the septentrial, which track the same signals, is very, very good. And then the Javad and the septentrial, which don't track the same signals, so you have a Q and an X comparison, also has a nice fit. So that's I think that's very encouraging. So at the end of the day, what is the effect of having these relatively speaking small biases on the code? What is it going to do to a PPP solution? So what we've done is we've done 1 day, 24 reconvergences for all receiver types. And you can see here that the initial offset is smaller for the septentrial and the Novotel. And then as we go up, we have the green is the Trimble, and initial offset from the truth is larger, and it converges a little bit more slowly. Now the TOPCon, which had the misconfiguration, where we had multipath mitigation on, also has a larger initial offset and converges more slowly. So we haven't done any work to implement these code biases in our software, but it sure seems that it's important to do that. Now, moving to interoperability between GPS and Galileo. What we did is we did a double difference, zero baseline double difference, to see that the phases were aligned. Now, this is the second one we did, and we provided feedback to the receiver manufacturers, I guess 7 months ago. And the situation wasn't quite as good as it is now. We did have biases before. You can see here that the only receiver type that has a bias is the TOPCon, and it looks like they've got a sign problem. So they had a quarter cycle offset, and they subtracted it or added it rather than, they have a sign problem. And then we did the same thing. So that was L1, E1. And what we have here is E5A, L5. The sharp-eyed person will see that we're missing the TOPCon. We had a problem with the TOPCon, so we removed it. Otherwise, all the other receivers provide aligned data. Now we've got 7 days of GLONASS DCB average and standard deviation, GPS and GLONASS. And what we're hoping to show here is that the standard deviation of the DCB estimates over the 7 days are more or less compatible for all receiver types so that they're interoperable. The red dots are the differential code biases, and the blue bars are the standard deviations. This is the standard deviation of the differential phase rate, and so we use this to characterize the or the phase noise so that scintillation can be observed, and we see interoperability again. So coming to the summary, we have common signal tracking of Galileo satellites between all receiver types not widely supported. So we're going to have intersignal DCB estimates. Showed you the effective range between, SNR range between receiver types, helping with interoperability. There was a movement about 10 years ago to try and standardize SNR estimation within the RTCM. It didn't go anywhere, so I guess we're stuck with different SNRs. We did inter-receiver code bias estimates, GPS biases between receivers tracking the same signals. Can be as large as 0.2 of a meter, 0.3 in some cases, and it affects the initial position estimate and convergence time. GLONASS biases, as I said, are in line with previous estimates. There's nothing new to say there. Initial Galileo bias estimates look very good. The phase alignment between E1, L1 and E5A and L5 are also aligned for most receiver types. Interoperability of the ionospheric measurements are characterized and they're interoperable. We'll continue to run these tests and share the data. This particular data set isn't the best one we collected because of the errors in the RTCM-MSM data. But once we get a good data set, we'll surely make the data available. And we plan to repeat these campaigns with new firmware. So that's pretty much it.